So now we begin our journey into chapter 10, which is liquids and solids. And basically, what about molecules dictates the properties of liquids and solids? And that journey starts with intermolecular forces. And so here you can read the learning outcomes and expectations. Feel free to pause and read through those. But let's dive right in. And so again, our journey into liquids and solids starts with 10.1, which is intermolecular forces. And so what we're starting with is intra versus inter. And so what we talked about in chapter 7 was largely intramolecular forces. And intra in this case translates to inside. And it's basically the interactions within a molecule or compound, right? This is the covalent ionic metallic bonds. That's what dictates the connectivity and how it goes together, and then the 3D structure of a given molecule. In contrast, you have something called intermolecular. And so inter in this case translates to between or among. And so when you have two independent molecules coming together, they can interact with each other. And it's not covalent, metallic, or ionic necessarily, but it's other forces that dictate how those molecules interact. And so while a single molecule has intramolecular bonds, and these bonds exist as covalent, ionic, or metallic, you can put two molecules together, like as the case here, like a DNA linkage, and these molecules interact with each other through intermolecular bonds and intermolecular forces. And so you can see the energy of these forces are very different. And so you can see the range for ionic, covalent, and metallic. You're talking, hundreds of thousands of kilojoules per mole. And then you look at intermolecular forces, and they're typically very weak. And so they're less than 100 kilojoules per mole, usually much weaker than these. So breaking a covalent bond is much harder than breaking a intermolecular bond. And so these numbers here, that's essentially the energy it takes to break apart a mole of those bonds or interactions. And so just to give you an example, if you're going to try to break apart an OH bond, which is a polar covalent bond in water, H2O, if you want to break apart 1 mole of these OH bonds, it's going to take you 930 kilojoules. So that's how much energy you're going to have to pump in to break 1 mole's worth of OH bonds. In contrast, if you want to take, 1 mole of water, which has hydrogen bonding and dipole-dipole interaction, to break up the interaction between H2O molecules, that is, have an H2O here, have an H2O here. If you want to break that apart, it's only going to cost you 41 kilojoules per mole. And so again, these numbers right here emphasize the difference between, say, a covalent bond and a dipole-dipole or hydrogen bonding interaction. And that's what's dictating the range of these energy values. And so when you talk about intermolecular forces, there's only so many things that can interact. You can have ions that interact, you can have polar molecules that interact, or you can have nonpolar. Remember, nonpolar, all the dipoles cancel out. Polar, there's an overall molecular dipole, and then ions are just charged species that have positive and negative charges. And so when you do the math on the number of ways things interact, ions can interact with ions, polar with polar, nonpolar with nonpolar, but also you can mix and match these interactions. And so you can have something called instantaneous induced dipole, you can have dipole-dipole, you can have an ionic bond, but you can also have an ion interacting with the dipole, or a negative charge interacting with positive. You can also have a polar interacting with a nonpolar, giving you these dipole-induced dipole bonds. And so as you saw earlier, the strongest bonds are typically here, the weakest bonds are typically here, but depending on the type of interaction, we have different nomenclature to describe what things are interacting, and that gives you a rough idea of the strength of the interaction. So the other one you can have is ion-induced dipole. And so here's the list in a different form. We have ions, we have polar molecules, we have nonpolar molecules or atoms. And so here's the list again. We have ion dipole, dipole-dipole, and something known as dispersion, which encompasses ion-induced dipole, dipole-induced dipole, instantaneous dipole, induced dipole. And so we'll just go through these individually. And so ion dipole is exactly what it sounds like. If you take an ion, something that's positive or negatively charged, and you throw it into a molecular species that's polar, so something where all the bond dipoles don't cancel out and you get an overall molecular dipole, you have a partial positive, partial negative. That partial positive is going to interact with the anion, the negative charge, and that partial negative is going to interact with the cation. And so it's an electrostatic attraction. You have something that's charged, formally charged plus, formally charged minus, interacting with something that has that partial, that lowercase delta, that less electron cloud here, more negative electron cloud here. That partial positive interacts with that overall negative. negative. And the strength of this interaction is directly dependent on the size and charge. And so the more charged something is, the more it wants to interact. The larger it is, the less likely it's going to want to interact. And so an example of this interaction is if you take sodium chloride, which is standard table salt, and you throw it in a cup of water, you are making millions and millions of ion-dipole interactions. And so the dipole comes from the water molecule, where it's partial positive on the H's, partial negative on the oxygens, and then you have a sodium plus, Na plus, and a chlorine minus. And so the minus interacts with the positive sides, the plus interacts with the negative sides. You have an ion-dipole interaction. And so, like I said earlier, the larger the ion, the lower the charge, the weaker the dipole, the weaker the interaction. And so you can think about this as simple electrostatics, right? The more positive and negative something is, the more attracted they're going to be. Anything that weakens that charge or weakens the proximity is going to weaken that interaction. And so larger ions, they have more space between them. They're going to have a weaker bond. Lower charge, similarly, it's not going to be as electrostatically attracted. Weaker dipole moment on the polar molecule is going to have a weaker interaction. But you take something small that has high charge, like comparing sodium to magnesium. Magnesium 2 plus, it's a 2 plus charge versus a 1 plus. It's a smaller ion. This is going to have a stronger interaction with water than, say, a sodium ion does. And so, again, the smaller it is, the more dense the charge density is, the stronger this interaction is going to be. And it's just simple negative plus positive. The more negative, the more positive, the more it's going to want to interact. And so the range on ion dipole, because it's an electrostatic attraction, is fairly large. It's typically 40 to 600 kilojoules per mole, depending on the nature of the ions that interact and the dipole that interacts. Now, dipole, as opposed to ion dipole, where with an ion, you have something that's formally positive, formally negative. A dipole-dipole interaction is basically where you have two things that are partially polar, right? They have polar covalent bonds that the dipole moments don't cancel out, and you have an overall polar molecule. The partial negative side interacts with the partial positive with negative, partial positive with negative. It's still electrostatics, but you're not having a formally charged species. There's not an anion or cation. There's not a negative or a positive. There's only partial positive and partial negative. And so the larger this dipole, the stronger the attraction. Just like ion dipole, the more charged it is, the more strongly attracted those negatives and positives will be. And so you basically have, especially in solution, you have all these molecules floating around. One half of the molecule is positive, one half of the molecule is negative. And basically you have this mix and match of alignments where positives try to be near negatives, positives try to repel each other, and it's just dynamically happening all the time. Those molecules are moving, but the overall goal is to minimize those positive and negative interactions and maximize positive negative. And that's what it's trying to do with dipole-dipole attraction. And so this one is less energetic than, say, an ion dipole. It's not as centrally charged as, say, an ion or cation or an anion, but it's still electrostatic. And so it's relatively, it's weaker than ion dipole, but still relatively strong. It takes 5 to 25 kilojoules per mole to break this electrostatic interaction between dipole moments of molecules. All right, so we covered the ion dipole. We covered the dipole-dipole. So ion dipole is exactly as it's described. Take an ion, mix it with a polar molecule that has a dipole. You take a dipole molecule with a molecule that has a dipole with a molecule that has a dipole, or a polar-polar interaction, and you get the dipole-dipole interaction. Now, there's another subcategory called dispersion forces. And this is basically the nonpolar molecules and how those nonpolars interact. And so the question is, if you have a nonpolar molecule, how can it have an electrostatic attraction, right? It doesn't have a negative charge. It doesn't have a positive charge. And so it does it through two different processes. One is called an instantaneous dipole, and the other is called an induced dipole. And so an instantaneous dipole basically says atoms and molecules are not static, right? They're constantly moving. They're in motion. Not only that, but the electron cloud isn't as rigorously defined as you'd like it to be, right? It's able to move around. And so what happens sometimes is an instantaneous dipole is the electron cloud shifts slightly. And so just a moment in time, just for an instant, that electron cloud shifts, and it's more electron rich on this side than it is on this side. And so here you get a partial negative, here you got a partial positive. Now this is going to return back to its original, non-polar form, but for a moment it's going to have this instantaneous dipole. And so that instantaneous dipole has a slight charge and it can interact. An induced dipole, in contrast, is not just a spontaneous thing, but instead you take a nonpolar molecule and you put some kind of charge in proximity to it, like you put a sodium ion versus next to something that's nonpolar. It's going to basically perturb this electron cloud. And so what's going to happen is if you have, say, a positive charge here, it's going to shift that cloud so the negative goes towards the positive, and you're going to get a temporary dipole moment that's partial negative and partial positive. And so it's called an induced dipole because something's causing this dipole. This one's called an instantaneous dipole because it's just spontaneous. It's just happening in the system. And so what this instantaneous and induced dipole does is it gives you a nonpolar molecule that's temporarily charged. It has a temporary negative, temporary positive, and so a nonpolar molecule can interact with polar or charged species. And so if you take an ion and put it with a nonpolar molecule, just like we described earlier, ion is always charged. It's going to temporarily shift this electron cloud. And so it's going to give you something called an ion-induced dipole interaction. And so here's the ion. Here's a nonpolar molecule that temporarily has an induced dipole. And so it induces partial negative this way, partial positive this way, and that's an electrostatic attraction. You can have the same thing with an anion, where you have your negative charge. There's your partial positive attracted to the negative, and your partial negative over here. So it actually shifts electrons that direction and gives you a temporarily charged nonpolar molecule. And so these are typically on the order of 3 to 15 kilojoules per mole. Now you can have the same thing happen with a polar molecule. So you take a polar molecule with a nonpolar molecule. That polar molecule, while not formally charged like the cation and anion, it does have partial charge. And so if there's a partial negative here and a partial positive here, that partial positive is going to attract electron density. So this nonpolar molecule or atom is going to shift its electrons, partial negative plus partial negative. There's a favorable interaction here. And then on the other side, you're going to have a partial negative, and so on and so forth. And so you can do the same thing the opposite direction, partial negative, partial positive. There's how it's going to interact. But the idea is this nonpolar molecule in the presence of either an ion or a dipole temporarily shifts that cloud in what's called an induced dipole. And so you have ion-induced dipole, you have dipole-induced dipole. And you can see the range of dipole-induced dipole energy from 2 to 10 kilojoules per mole. This one's a weaker interaction, and it should be, right? Because if we're thinking about just electrostatics, how positive and negatives go together, this is a formal positive and negative. It's going to be much more attractive than, say, a partial positive, partial negative. This is going to be much less of an electrostatic interaction. The other one you can have is a nonpolar molecule interacting with a nonpolar. And so remember, we talked about an induced dipole, where you have an ion or a dipole moment inducing a dipole in a nonpolar. Well, you also have instantaneous dipole moments. So remember, we talked about this cloud just spontaneously moving sometimes. Well, if that cloud spontaneously moves, then you have a temporary partial negative, partial positive. And so if this molecule or this atom has a partial negative, partial positive, it's in proximity to another nonpolar molecule, it's going to induce a dipole moment. And so essentially you're going to have an instantaneous dipole, and then it's going to induce a dipole in the adjacent molecule, much like the ions and dipole moments did. And so while nonpolars are not going to electrostatically attract when they're nonpolar, if they have an instantaneous dipole, they can actually shift their electron density. And so this is what we call an instantaneous induced dipole. And so this is instantaneous, it just happens, and then this should actually read induced dipole. So you have an instantaneous inducing a dipole, and then it propagates through. So if you have another nonpolar here, another nonpolar here, it's going to induce a charge throughout that. And so you can have an electrostatic interaction between nonpolar molecules, and it's temporary, which is why it's called instantaneous induced dipole. And so this has a really wide energy range from 0.05 to 40 kilojoules per mole, and it really depends on the size of the molecule and the nature of that electron cloud. And so the phrase we're looking for to describe that is something called polarizability. It's basically how easy is it for a molecule or atom to shift this cloud. If it's really easy, it's going to be highly polarizable. It's going to have strong instantaneous induced. If it's not so easy to shift that cloud, it's only going to have weak instantaneous induced, and it's dictated by the polarizability of the molecule or atom. And so it's basically, yeah, you can read the formal definitions, but how easy is it to move that electron cloud? And so just some general rules. The bigger the cloud, the easier it is to distort. So the bigger the atom or molecule, the more polarizable, the stronger instantaneous induced interactions. And so here you can see the trend on the periodic table. If you go from CH4 to CF4, CL4, CBr4, CI4, you're getting bigger and bigger as you go down the table. This is a huge molecule, and you can see the melting temperature goes up. It's harder to break these interactions because this is much more polarizable. And so general rules, it increases left to right across the periodic table. But yeah, it all comes back to this size idea. How big is the electron cloud and how much can that electron cloud polarize? And so this is a really cool example. We have neopentane, isopentane, and N-pentane. And so all these, it's C5H12, same formula, different connectivity. So N-pentane is in a long chain. Neopentane is basically a tetrahedral geometry of carbon atoms. And so you can see this is like a ball and this is like a noodle or a long string. And so this one is going to have stronger intermolecular forces because it has higher polarizability. You can think about this cloud being very long. This cloud can polarize down the entire axis, whereas this can only polarize in a localized way. And so the bigger the surface area, the longer the molecules, the larger the cloud, the more polarizable it is, the stronger those intermolecular forces. And so this is why things like, methane is a nonpolar molecule, very weak interactions, it's gas at room temperature. You take something like octane, that's in gasoline, that's a liquid at room temperature, it's an 8-carbon chain, and then you take something much longer, which is essentially candle wax, is made up of longer carbon chains. And so the longer those chains get, the stronger those interactions because of the higher polarizability, which is why wax is a solid at room temperature, gasoline is a liquid, and then methane gas is in the gas phase at room temperature. And it's the same idea. How big is it and how polarizable is that cloud? And so, yeah, that covers the major categories. You have an ion dipole, you have a dipole-dipole, and then you have the dispersion forces. And so if it's a nonpolar molecule interacting with any, it'll be this category. If it's a dipole with the dipole, it falls here. If it's an ion with a dipole, it falls here. Now, one last category that's really important to discuss is hydrogen bonding. It's basically a special case of dipole-dipole interaction. And so we talked a lot about periodic trends, right? When you go down the periodic table or up the periodic table, the things are expected to behave in a certain way. And so the same thing's true with intermolecular forces, right? So if you look at boiling point as you go up the periodic table, H2Te to H2Se to H2S, it has a trend. And this trend roughly correlates with the polarizability of the molecules. And so all these are the same geometry. All you're changing is the atoms that are associated with each other. So Hi to HBr to HCl, it becomes more polar, stronger dipole-dipole interaction. Same thing with these guys. And so if you were going to predict what happens next as we move up the periodic table, if we move to H2O, HF, and NH3, you'd expect this to stay linear. But that's not what actually happens experimentally. Instead, it goes this way. And so we have this really nice periodic trend. It's really accurately described with dipole-dipole interactions and the decreasing boiling point with the increasing strength of that interaction and the polarity of the molecules. H2O, HF, and NH3 completely break that trend. And in sciences, it's great. Anytime we love fitting things with straight lines because straight lines tell us we have a trend. If something doesn't fit that trend, it's because some new phenomena is occurring. And that's exactly what's happening with H2O, HF, and NH3. And so the question is, what is it? We clearly know it's not just dipole-dipole. There's something else that's going on. And the answer in this case is hydrogen bonding. It basically says that if you have a hydrogen atom attached to an N, O, or an F, and a lone pair on an O and an F, and generally these electronegative atoms, you can generate something known as a hydrogen bond. And so what basically happens is you have N or F attached to an H. And so you have this covalent bond, but it's not too strong of a bond. And so what happens is if you have an N or an F with a lone pair on it, you can generate something called a hydrogen bond. And we draw it in the form of a dot or a dash between those atoms. And so this interaction, 10 to 40 kilojoules per mole, it's basically a dipole-dipole interaction where you have partial positive here, partial negative here, and partial negative here. But because the lone pair and the H can interact in kind of an acid-base chemistry type way, it ends up being a stronger interaction than just dipole-dipole alone. And so here's some examples of some hydrogen bond donors where you have an F and an H. Again, the rule is just, is the H attached to an O, N, or an F? And so any of these can donate a hydrogen. You can also have hydrogen bond acceptors, where basically there's a lone pair. So on the end of the cyano group, there's a lone pair on the oxygen, lone pair on these oxygens, lone pair on this aldehyde or this amine. These lone pairs can interact with this H, and you can draw this dashed line, which is a hydrogen bond. And so, yeah, it's a very particular interaction. Again, it's dipole-dipole, but you need to have an H and a lone pair. And so as long as there's an H attached to an O, N, or an F, and a lone pair on an O, N, or an F, you can have a hydrogen bond. And so one thing to note is that the N, O, or F must have a lone pair. And so here's an example. If you take CH3, well, 3 CH3s around a nitrogen, this trimethylamine, it has a lone pair. This guy can do hydrogen bonding. If you put 4 of those CH groups around it, there's no longer a lone pair. This can't hydrogen bond. So it's not enough for an NO or an H to be, or an F to be present. You also need a lone pair that can interact. And so you can have favorable interactions here. You can have favorable interactions with this if you have an H donor, but this guy doesn't have a lone pair, so it can't do hydrogen bonding. So just quickly going back to this graph, again, you had this trend of dipole-dipole interaction, and then something weird happened. You end up with H2O, HF, and NH3, which have higher boiling points than you'd expect from dipole-dipole alone. And the reason is these guys can hydrogen bond. They have lone pairs on the oxygen, fluorine, and nitrogen. They also have H's that can interact with those lone pairs, and you can generate this hydrogen bonding interaction. And so, yeah, you need the lone pair. You need an H attached to an NO or an F. And if you have those parameters, then you can generate a hydrogen bond, which is stronger than just dipole-dipole alone. So yeah, there's our list. Ion with a polar molecule, polar with polar, nonpolar with ion, polar or nonpolar, and then you have hydrogen bonding, which is a special case of dipole-dipole, where you have polar, but you have an NH, N, an F, or an O with an H attached interacting with a lone pair from an N, O, or an F. And so yeah, you can have hydrogen bonding. All right, so there's the summary. There's the different possible ways you can mix and match these guys. And so ion with ion is an ionic bond. That's an intramolecular force. We're going to ignore that for now. But if you have an ion with a polar, that's ion dipole in green. If you have a polar with a polar, that's dipole-dipole. If you have a nonpolar with a nonpolar, that's instantaneous induced dipole. If you have a nonpolar with a polar, dipole-induced dipole. And then an ion with a nonpolar, that's the ion-induced dipole. And so, yeah, that's a lot of words to throw at you, but basically anytime it says the word ion, it's describing a charged species interacting with something, whether it's polar or nonpolar. If you have a dipole, that's describing a polar molecule interacting with something, whether it's an ion or a nonpolar. And then you can have a nonpolar interacting with either an ion, nonpolar, or a polar and a nonpolar. And so, yeah, it's nomenclature, but when you identify which species are interacting with each other, then you can assign those intermolecular forces. And some textbooks, and you can search the web for different versions of this, but basically there's flow charts. You ask, are ions involved? Is it an ion plus a polar molecule? Then you can assign the interactions as ion dipole. Or you can say, okay, are ions involved? No. Are there polar molecules? No, it can only be instantaneous induced. If there are polar molecules, can it hydrogen bond? Yes, it's hydrogen bonding. Can it do, or if not, then it has dipole-dipole. And so again, it's just what two things are interacting, and then you name those things. And then ultimately, when you name them, you get a rough idea about the strength of those interactions. And so here's just a general idea, like we talked about earlier. Ions are going to have the strongest interaction because they're the most charged species. Then hydrogen bonding will be next. Then dipole-dipole. Remember, dipole-dipole, hydrogen bonding is a special case of dipole-dipole, but it's dipole-dipole plus a little extra. And so that's why it takes more energy to break a hydrogen bond than it does a dipole-dipole. And then you have the nonpolar interactions. And so generally these are going to be weaker, with the ion being the strongest, dipole being second, and then instantaneous induced being the weakest. But if you get big enough molecules, this number can start getting very, very large, and you can start having solids at room temperature. So yeah, that's the summary. Basically what we've done is we've gone through a journey. We take a molecular formula, we turn it into a 3D structure. From that 3D structure, we can use the polarity of the molecules. We can assign it as polar, nonpolar, or ionic. And then from those defined species, we can say which two things are interacting and how do we define those, whether it's a polar with a polar, nonpolar with nonpolar, polar with nonpolar, so on and so forth. That tells us the type of intermolecular force. And from those intermolecular forces, we can estimate, what's the relative strength. Even within a trend on the periodic table, we can say, how strong is this interaction? And that's going to dictate properties, as we'll talk about in the remainder of this chapter. So yeah, that closes out 10.1 intermolecular forces. Then we'll dive into properties of liquids, phase transitions, and diagrams.